hopefully you remember back to general chemistry, the reason why I placed these electrons where I did in the orbital energy diagrams. But let's quickly go over the rules that are governing why I placed them where I did. All right, so the first rule is something called the off-bow principle, which is you fill up your lowest energy orbitals first. And when we drew these orbitals, I'm going to jump back for just a second. I drew them very specifically from lowest to highest energy. And that's typically, for organic chemistry, usually 2p is about as far as we need to go. So the 1s is the lowest energy, the 2s is the second lowest energy, and the 2p is the third lowest energy. And we've got those three 2p energy, 2p orbitals. So off-bow principle, this guy right here. Off-bow principle states that you fill from your lowest energy orbital up. So you start at the 1s, you fill in, and then you keep going up. So, and then I have my order 1s, 2s, 2p, 3s, 3p, 4s, 3d. That's different. We'll get to that in just a minute. Rule number 2 is that you can have no two electrons occupying the same orbital in the same spin at the same time. So this is saying that you have up and down, right? Up and down spins, which is why I drew the arrows up and down. And if you're going to have two electrons in any orbital, they must be of opposite spins. They must be spin paired. And this is called the Pauli exclusion principle. It's saying that you can't have two orbitals with all four of the same quantum numbers, or you can't have two electrons with all four of the same quantum numbers, two electrons with the same spin in the same orbital at the same time. All right, and then rule number 3 was if you have two or more empty orbitals of equal energy, instead of filling an orbital completely with two spin paired electrons, you'll put two parallel spin electrons in those two degenerate orbitals and half fill them. This is called Hund's rule. I'm not particularly worried that you know the names of these rules. You just know that what this rule states is that instead of filling one orbital completely with a spin paired, you fill two orbitals half with spin parallel. That is both up or both down. Doesn't matter. Electrons tend to be unpaired to the maximum extent. And the way you can think about this is if you have two electrons, they're both negatively charged. They don't want to be occupying the same space because the negative charges repel each other. Like charges repel. All right, so we could draw some electron configurations for each one of these atoms. Right, and let's do nitrogen first. Nitrogen, I'm going to start with a 1s, 2s, 2p. Nitrogen, 7 protons means 7 electrons. 1, 2, 3, 4, 5, 6, 7. Phosphorus, 15. 1s, 2s, 2p, 3s, 3p. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. C6, 1s, 2s, 2p. 1, 2, 3, 4, 5, 6. Notice, as in all of these, I'm filling from the bottom up, right? I'm never putting two of the same spin electrons in one orbital, and when I get to degenerate orbitals, I'm putting them spin parallel in first, and then I'll go back and fill them if I have enough. So Cl17, 1s, 2s, 2p, 2, 3, 3s, 3p, 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So now we move on to something called formal charge. And formal charge is a way of keeping track of situations where you have extra electrons that are giving you atoms that have an imbalance of electrons and protons and thus have a total formal charge. So if you have more electrons than protons in a molecule, then you're going to have a formal negative charge, and if you have more protons than electrons in a molecule, you're going to have a formal positive charge. Now, we typically, for organic chemistry, we need to assign these for given atoms, so there's a way we go about doing this. We do this with this equation on the bottom, right, which is formal charge is number of lone pair of electrons minus 1/2 of the number of bonding electrons. And that whole number is subtracted from the number of valence electrons. So let's take a look at that. If you have something like hydroxide, HO minus, hydroxide looks like that. Just make my H a little bit better there. We're going to find out that for the oxygen, it has a negative formal charge. And one way that you could come about doing that is saying oxygen, according to the periodic table, should have 6 valence electrons minus 1, 2, 3, 4, 5, 6 lone pair electrons minus 1/2 of the 2 bonding electrons, so minus 1. 1 for 1/2 of the 2 bonding electrons. And that gets us to a total number of minus 1, and that means that the total charge on the oxygen is minus 1. Now, I've got a few examples of this, but keep this equation in mind. Number of valence electrons minus number of lone pairs minus 1/2 of the number of bonding electrons. So here we go. Here's a couple of examples where we can determine formal charges on different atoms. So you take a look at each one of these atoms, and so in order to do that, the first thing we have to do is draw out the complete Lewis structure here. So in this case, hydronium, the Lewis structure looks like this. And if you do a formal charge calculation, the hydrogens, right, each one of the hydrogens should have, according to the periodic table, 1 total valence electron. And if you do that formal charge equation, right, number 1 minus number of non-bonding electrons, 0 for hydrogen, minus 1/2 of the shared electrons, 1 total for hydrogen, because there's 2 shared electrons, so this is, the H's in all of this have a formal charge of 0. Oxygen, right, is 6 minus, in this case we have 2 non-bonding electrons, minus 1/2 of 1, 2, 3, 4, 5, 6 shared electrons. So minus 6 divided by 2. So this is 6 minus 2 minus 3, which is equal to 1. Plus 1 specifically. So this is the positive charge on hydronium. All right, if you look at NO+, put my lone pairs here. Let's do the formal charge for each atom in NO+. All right, so nitrogen should have 5 valence electrons minus 2 lone pair electrons minus 1/2 of 3 sets of bonding, or 1/2 of 6 shared electrons, so minus 3, which is equal to 0. So nitrogen has a formal charge of 0. Oxygen, on the other hand, should have 6, and it's going to be the same situation here, minus 2 lone pair electrons, minus 1/2 of 6 shared electrons, so minus 3. Oxygen is equal to plus 1. Positive charge on the oxygen here. All right, formal charges are important. Formal charges are important because they keep track of where the electrons are in a molecule. So this is a good skill to have, and you're going to want to be able to work through this formal charge equation pretty quick and easy. Oh, there you go. Okay, so next thing we're going to do is bonding patterns, because bonding patterns are going to give you the sort of quick answer to the formal charge question. So if you look at the first row of atoms, actually the second row of atoms in the periodic table, you'll see over on the right hand side there are boron, carbon, nitrogen, oxygen, and also fluorine. And these are the ones that we really pay attention to. These are the atoms that we pay the most attention to in organic chemistry. So knowing the general bonding patterns of these guys is going to be pretty important. And you'll get to the point where you're very familiar with these, just because you've seen them so often in organic chemistry. But let's take a look at them, and let's take a look at the typical bonding patterns for them. Boron has 3 valence electrons. And so I mentioned on a previous slide that if you have 3 valence electrons, you can pair up those 3 electrons and you get a total of 3 bonds, right? And then boron is neutral with just 3 bonds. And that means that boron has no octet. It doesn't have a complete 8-electron octet. This is one of the few cases where this is okay. And we won't run into it all that often. Sometimes you'll see boron with 4 bonds, but in order for boron to have 4 bonds, it has to have a negative charge. So a negatively charged boron is going to have 4 bonds, and that's it. And we don't see positively charged boron, so don't even worry about that. Carbon's the big one. Carbon always has 4 bonds. Carbon can have 4 bonds and be neutral, but carbon can also have 3 bonds and a lone pair, and then it's negatively charged, or 3 bonds and no lone pair, and then it's positively charged. But once again, if it's 3 bonds and no lone pair, you don't have a complete octet, right? You don't have 8 electrons around that carbon. Nitrogen usually has 3 bonds and a lone pair, and it's neutral in that scenario, and that's because, once again, it has 5 valence electrons. It only needs to pair up 3 of them to get to a complete octet, and as long as it's paired up 3 of them, it's got a neutral formal charge. If it has 2 bonds and 2 lone pairs, it's negatively charged. If it has 4 bonds and no lone pairs, it's positively charged. You can do the formal charge equation to work that out for yourself. That works. The same way, oxygen usually has 2 bonds. So oxygen will have 2 lone pairs typically. Right, here we go. That's neutral. If it has 3 bonds and 1 lone pair, then it's going to be positively charged. If it has 1 bond and 3 lone pairs, it's going to be negatively charged. The halogens usually have 1 bond, so you're seeing a pattern from carbon on down, right? We've gone from 4 to 3 to 2 to 1 bond under their neutral conditions. So halogens are typically 1 bond and 3 lone pairs. They can have 4 lone pairs and no bonds, and then they're negatively charged, or they can have 2 bonds and 2 lone pairs, and they're positively charged. These common bonding patterns will get you the formal charge if you just know them. Carbon always has 4. Nitrogen usually has 3 bonds and more or less will give you a charge. And oxygen usually has 2 bonds and more or less will give you a charge. Chlorine usually has 1 bond, or halogens in general usually have 1 bond and more or less will give you a charge. So here's some practice. These are pretty straightforward. Here's nitrogen with 4 bonds and no lone pair. And that, if you look back at the bonding pattern screen, should show you that you have a positive charge. We can also do the formal charge equation. Nitrogen normally has 5 valence electrons minus 0 lone pair electrons minus 1/2 of 8. So 4 bonding electrons is equal to plus 1 plus 1. This one's neutral, and this one's negative. And you can do the negative 1. You can do the math to determine that yourself. Then when you look at oxygen, right, we can do the formal charge again on this to see that oxygen usually has 6 valence electrons minus 2 lone pair electrons minus 1/2 of 6 bonding electrons, so 3, and that's a total of plus 1, right? So this is a positively charged oxygen. Here we have oxygen, which is normally has 6 minus 4 non-bonding electrons minus 1/2 of 4 bonding electrons, or 2, which is equal to 0. So this is a neutral oxygen. And here we have oxygen with, normally has 6, right, minus 1, 2, 3, 4, 5, 6 non-bonding electrons minus 1/2 of 2 shared electrons, so minus 1, and that's equal to -1. So this is a negatively charged oxygen. So one thing to point out, you've seen me do this already. If it's just plus or minus 1, I drop the number all the time, and I just say plus or minus. If I drop the number, I'm indicating that it's plus or minus 1, right? And that's pretty much it. Okay, here is a practice MCAT question, and this MCAT question is going to test your ability to draw Lewis structures. And the point of formal charges and Lewis structures is the best Lewis structure is typically one that minimizes the number of formal charges. So if you can have a completely neutral Lewis structure where no atoms have formal charges, that's going to be the best Lewis structure. So what we're going to do here is go through and calculate the formal charges on each one of these atoms. And I will let you do that, right? That's a good practice question. I'm going to tell you what I get just by looking at bond patterns. So when I look at this oxygen, it has 1, 2, 3 bonds and a lone pair. That should be a positively charged oxygen. This should be a positively charged oxygen. And this is a carbon with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 electrons around it. And that's not an octet. That's well more than an octet. So this is a terrible Lewis structure. A, because it's got 2 positive charges, and B, because that carbon has 12 electrons around it. Something is totally wrong with that. All right, if I look over at B, right, here is a oxygen that looks like it's neutral, right? This oxygen looks like it's neutral. This carbon looks like it's neutral, just based on bonding patterns, right? This carbon has 1, 2, 3, 4, 5, 6, 7, 8 shared electrons, so 4 valence electrons minus 1/2 of the number of shared electrons is equal to a neutral charge, 0 charge on the carbon. All right, so that in mind, this is a pretty good looking Lewis structure. All the octets are complete. I've got everything with neutral charges. So this one is probably going to be right. But let's go back and let's go do the other ones too, just to make sure that we can prove it to ourselves. All right, here is a Lewis structure where the carbon has 4 bonds, which means the carbon's neutral, it has a complete octet. This oxygen is positive because it's got 3 bonds and 1 lone pair. This oxygen is weird. It's got 1, 2, 3, 4, 5, 6 electrons around it. So this one has an incomplete octet. And that's a no-go for Lewis structures. Don't draw Lewis structures with incomplete octets. This is not the right answer. All right. On that vein, right, here's an oxygen with 6 electrons around it. Here's an oxygen with 6 electrons around them. Both of these have incomplete octets. What? Don't do that. Incomplete octets. So this is also a no-go. So the answer here is B, right? B is the correct answer, the correctly drawn Lewis structure of carbon dioxide.